Okay, welcome everyone to my continuation of what are my favorite theorems, my usual bias perspective, of course. Today, I actually won't tell you a single theorem. It will be more like a definition, and the definition will be the theorem itself. It's kind of a very nice idea that goes back to this, by now, probably very popular small world experiment, effect, whatever you want to call it. This everyone knows everyone, so we will go into some details in a second. And it's actually not so clear how to make this kind of mathematical, to how to treat what you can observe in experiments in kind of a mathematical fashion. And that's the theorem today, right? It's like the definition how to do this in terms of graph theory, in terms of random graph theory, something like this. We will see. But let's get started, actually. Okay? Let's just jump right into it. So the small world experiment is actually pretty old by now, or whatever old means. It's probably very recent if you just consider the history of science itself. So it goes back to the mid-end of the 60s. And the original experiment is kind of very brilliant, and it turned out to be true in various cases that we will discuss, a few of them that we will discuss here in the video. And kind of just was this idea of how many steps are humans separated. So I would like you to keep in mind is that we have some kind of graph, and the nodes are the humans, and kind of the connections between them are, well, whether they know each other in whatever kind of sense, whether they know each other. So this one here in the middle, for example, this one here, they know this guy, this guy, this guy, and this one here. So it would have four neighbors. So the one in the middle, as I said, just knows four different people, and this one here knows three different people, and so on. There could be some rather isolated people, whatever, right? So we have a graph in mathematical terms, and the vertices are humans, or whatever you want. We will see some examples in a second, as I said. And in this original experiment, what they tried is they tried to see how this graph looks like. So how would you do that? Nowadays, I think it's pretty simple, but in the 60s, it wasn't quite so clear. So not just it was a brilliant idea just to do it, right? This could be a thing. It's kind of a brilliant idea already. And it's one of the most cited papers in the history of science. So this should tell you something, right? But also how to do it is not quite obvious. So what they did is they sent it mail. So not email. So we are in the 60s, right? They sent it mails, the really just hard copy. They sent it them from, well, I took here, I think, the experiment, the later one from 69. So they sent mails from, well, Nebraska to Massachusetts, or from Boston to Massachusetts. And I counted the number of steps it would need for the mail from the first sender to come to the last one, right? So kind of on average, they had something like 5.2 steps, which is pretty amazing. Keep in mind that they were sending around mails, and it was the 60s, right? It's not like everyone knew everyone via Facebook or whatever. No, it's the 60s. It's not so easy to go from Nebraska to whatever. And it still took them only 5.2 steps. This experiment from one of the standards was a little bit, fishy, let's say, because, well, they sent it quite a lot mails, right? So what would you do? You're in the 60s, you get a random mail from someone. Please send this mail further to someone else, closer to this guy. Would you do it? I'm not sure whether I would do it, or I'm not sure whether I would do it. So they sent it around quite a few mails, and not many made it. So it wasn't a really good sample size here anyway. But the experiment was repeated several times, so it's pretty sound by now. Nowadays, it's of course much easier. You could send around emails, and instead of sending 100 mails or whatever they did, you just send 100,000 emails. Most of them will probably be ignored, but there will be still a good number that actually will make it. And probably this 2.5 steps, this distance between the humans here, it probably will be lower nowadays. But anyway, in the 60s, that's what they got. So this is, by the way, where this 6 degree of separation comes from, which is kind of very popular in popular science. Yeah. So 6 degrees of separation. It kind of comes from this experiment, although the experiment itself never coined that term. So the term came up later. Anyway, so this suggested actually that human society, in some sense, is a small world network. And this whole video is kind of about trying to nail down what a small world network could be. So what is this actually, right? What could be a small world network? Kind of in our brains, because we have seen it so often by now, I guess. So small world is very popular. You can imagine what it is, Facebook connections or whatever, something like this. I show you some examples on the next slide. But to make this mathematical, to find a good mathematical definition, that's not so obvious. So what mathematically speaking is a small world network? And the definition itself will be the theorem for today. Anyway, so let me repeat what we just said here. So in the 60s, there was this very, very famous, it's called Milgram experiment. I should have said that before. And it was about sending mails around. Again, it was the 60s. People were sending hard copy mails around. And it was kind of a questionable experiment, but it was still pretty brilliant. It was repeated several times. And it actually works. So roughly, it took let's say 5 steps. So the degree of separation here was kind of 5. And this means the following. So for any person, there should be 5 steps. 1, 2, 3, 4. This is actually closer here. Whatever, 1, 2, 3, 4, 5. There would be on average 5 steps to go to a given person, to given different person in the graph. That's kind of what should be a small world network. And as I said, they kind of repeated this experiment several times. And nowadays, in particular with the internet, we know several examples of small world networks. I will give you a non-example in a second, but for example, Wikipedia is a small world network in the sense that, well, the nodes are the pages of Wikipedia, the edges are the links from jump around between different pages. And it's actually, you can go very, very fast from one page to a random other page, basically. So it's kind of a small world network. Here's a famous example is there's a mathematician called Paul Erdös, probably pronouncing it completely wrong, but anyway, it doesn't matter. And there's a person called Kevin Bacon, and they are related by 2 steps. So from Erdős's website, you can, well, click on a link, and you will go to the Erdős number, which I'm going to explain in a second, and you will go to small world experiments. Very, very nice. So this is the one, this is kind of underlying this video, and from both you should go to Kevin Bacon. And the relation is as follows, kind of a little bit of a fun story. So Erdős at one point proposed kind of a way to measure the distance of the network of mathematicians in the following way. So the center of the universe is Erdős itself, which is a bit questionable, but anyway. So let's say the center of the universe is Erdős, and the vertices of my graph are the mathematicians, and you draw an edge between them if they have a shared collaboration. So if they have a kind of a shared research paper, research publication, you would draw an edge between them, and that's what you call the Erdős number. And so kind of every mathematician should get an Erdős number. The problem with this concept is obviously kind of not everyone has a finite Erdős number, right? So if you have never published anything, your Erdős number by definition would be infinity. People came up with different variations, and I just call this a collaboration distance. So the Erdős number would be the collaboration distance among mathematicians. There are versions for other sciences. There is a version for actors. So you can kind of draw an edge between actors if they appeared in the shared movie, for example, and you would get something like the Bacon number, because now Bacon apparently is the center of the universe. So kind of measure the distance between different people. You could also, of course, measure the difference between anyone else. So you could also say actor number X is the center of the universe, whatever you want. But anyway, collaboration distances tend to be small world networks. So you're usually, if you're a mathematician and you have published a paper, you're usually not very far away from Paul Erdős. If you're an actor and you've acted in some movie, you're usually not very far away from Kevin Bacon or any other mathematician or any other actor. The Wikipedia distance, as I already explained before, so Wikipedia is really, really small. Various other social networks, Facebook or whatever, they're usually also very, very small. Just on Facebook, it's so easy to be friends with someone, right? So it's just anyway, and of course, much more interesting, maybe also networks that behave a little bit like the internet, like the World Wide Web, kind of brains and so on. That's kind of nice. I will come back to that later on. A little bit surprising. So the brain is a little bit like the internet. Kind of a fun story, and many, many, many more. And there are also non-examples. So let me give you one non-example. So you could measure We already mentioned kind of the distance, how far humans are apart. So this was this picture here. But you can also measure how far humans are apart throughout the history of humankind. And you can draw a network. And this can't be really a small world network. Why? Well, let's say we are living here in whatever it is, 2021, and you would need a path from, let's say, me to someone who lived whatever 4,000 years before Christ, something like that. And this just needs to be very far, right? I mean, I need a certain number of steps to get there. So this is a non-example of a small world network. It's not a small world network. So the human society, if you take all ages together, it's not a small network, a small world network. The human society itself usually tends to be one. And so, kind of, what is so special about small world networks? That they appear in many places, and how can we treat them mathematically? Yeah, so let's do some mathematics actually. And this is kind of a pretty cool idea. It's not so easy to get it done in practice. There will be some catch. I will explain that on the next, but just from the idea, it's pretty nice. So you kind of want to be a small world network to be kind of the best of two extremes. And the first extreme would be something that is lattice-like, that is ordered. Think of kind of very simple example, just a graph, which is just a circle. It's a very ordered graph, right? And on the other hand, a random graph, which is kind of the opposite. It's disordered. It's random, right? So just think again about points on the circle, but now you kind of draw random edges between them, and of course it can get whatever random. That's the whole point. And the small world is in some sense what is lies in between, and it should have kind of the properties of both at once. So a small world in between. So it's not ordered. It's a bit more complicated than ordered, and it's a bit more ordered than random, kind of in between. If you would like to give this a 0 on the level of randomness, and you would give this a 1 on the level of randomness, then this should be around 0.5, let's say. Precise numbers here doesn't matter. It's just the idea here. And what makes it interesting, or what kind of defines it in the end, we'll see the definition on the next slide, is there are two kind of numerical invariants, and it shares like this, and it shares like this. Okay, so it's really in the middle. So the one of them is the mean pass length, and that's exactly what we had here. So whatever, how far is this one away from this one, and how far is this one away from this one, and just take the average over everything. So the average distance of the graph, and that's kind of small in random graphs because they're kind of random edges everywhere. And even if you arrange them on a circle, kind of there will be random edges, and they just go everywhere and whatever, and you can jump very, very efficiently from one vertex to the other. And it's actually very big, so or very long in a circle, right? In a circle, it's, let's just say it takes an easy circle. It's kind of really long. Two opposite points, you need a very long edge or a lot of edges to go from two opposite points to one another, right? Between one another. And in a small world, it should be kind of in the middle. Remember this degree 6 of separation. So it's not as small as in a random network. Show you more explicit examples in a second, but it's not as close, not as far away as in an ordered network. And there's something else. So this is the short distance idea, but there's something else you would like to do, and that's kind of a little bit more subtle. But it's kind of this idea that my friends tend to be friends, right? So my friends tend to be my friends. This is for following idea of clustering. So if this is you, so your green vertex, and here are three examples. So an edge is now your friend. It's like this still this idea of how far humans are separated. So these are all your friends. They're all edged to you, right? So all the other vertices in this little example are your friends. And you ask, what is the connectivity among your friends? So high clustering, like here, where everything is just connected. So here, connected, it would be cluster coefficient 1. So this cluster coefficient should be a number between 0 and 1, which is kind of, you could think of it like the probability of your friends, my friends being friends. Very complicated. Anyway, and if you have missing edges, you get a smaller number here. That's kind of the point. So if you have no edges at all, so all of your friends, they don't know each other, then it would be cluster coefficient 0, and everything in between is kind of everything in between. And this is then just actually what really defines, or what was the original definition about 20 years ago from now. I said we're 2021, so roughly around the turn of the millennia. This really amazing paper linked in the description, which kind of defines mathematically what a small world network is. And they say the following. So a small world network is a graph, of course, such that the average path length is roughly the average path length. So it's my L in my notation is roughly the average path length of a random graph. But the cluster coefficient is much, much bigger than for a random graph. Turns out that for random graphs, the cluster coefficient is really, really tiny. Um, the only catch here is I will go to this definition of a local cluster coefficient in a second. There's also a global cluster coefficient, whatever. The only really catch is here that random graph kind of depends a little bit on the model used. So random is always a little bit fishy. You need to make that precise. It doesn't really matter for this video. We'll just go with it. But there's a slight catch here. There's some random graph needs to be made precise, but you can do it. So it's not a huge problem. It's just something you should keep in mind. Anyway, so there's this local cluster coefficient, and it works as follows. So you have your little graph here, and you count your number of friends. So you count the number of edges. So in this case, I would count 3. I have 3 friends. I have 3 edges. That's just 3. Okay, and this is this one here, the number of neighbors. And you should take this, let's say it's k, and you should take this times k minus 1. Okay, and divide by 2. So these are these numbers here. So k times k minus 1 divided by 2. For my example, k was 3. So we would get k times k minus 1 divided by 2 would be 3 itself. Okay? Okay. So 3 itself, and you would divide by this number. So whatever you write on top, you divide it by 3. And as you can see here in this example, so then you count the edges between your friends. So here are 3 edges between your friends. To divide 3 by 3, you get 1. Here's 1 edge. So here's 1 edge. You still have 3. So 3 stays fixed. Here's 0 edge. You get 0, of course. 1 divided by 3 is 1 over 3. So this is kind of this mathematical measure of the clustering. Though my friends' friends tend to be friends. This is the mathematical measure of it. And you would kind of compare this, and this is kind of what they actually did. So for example, there are very many examples. So my film actors example here, it was this Bacon number. There's quite a few, actually quite a big size that they measured here, so 200,000-ish. And average shortest path is actually pretty small. And it's comparable to a shortest path in a random graph. And the clustering coefficient is pretty high. That's what you want, right? Short average distance, high cluster coefficients. And it's just much, much bigger than the cluster coefficient in the associated random graph. And that determines a small world network. So film actors form a small world network. And they have many other examples. So here's another one. Instead of the Erdös number, they looked at some kind of some analog for medicine. So Medline co-authorship. There are quite a few people here. And the average distance is not so bad. It's 4.6. It's comparable to the average distance of a comparable random graph. The clustering is, as you can see here, and it's much, much bigger than the corresponding clustering for a random graph here. Yeah, so film actors form, as you can see a little bit from this data, film actors form a little bit denser, if you want, whatever that means, a small world network than the co-authorship in medicine. But it's kind of the same flavor, right? Shortest path, average shortest path is pretty short, and cluster coefficient is pretty high, both compared to kind of a random graph, right? So the average path length here should be roughly the same. So here. Okay, and then they did something else, not with some kind of bacteria or whatever. So you can play a lot of games here. And it's kind of surprising. Whenever you have this pattern here, it looks like this. So here's a huge difference. So it's a huge difference, and they are roughly the same here. Then you have a small world network. It's kind of the definition of a small world network, which is very surprising because, as I said, it's very exciting. As I said in the beginning, it's not quite obvious how to define small world network, but here is kind of the definition. Of course, you can vary the definition a little bit. The definition is never truth. The definition is not just a definition, but this is roughly what they did. And this paper has hundreds and thousands of citations. So there has to be something going on. So people then just try to find small world networks. And for example, the brain tends to be very often to form a small world network, kind of the idea that I stole from a paper linked in the description, how you should think about it. So we have this ordered network, and we have this completely random network, and the small world network is kind of in between. And an ordered network has this local efficiency because it's clustering, it's very clustered, but it has a very small global efficiency because it's kind of takes you a very long time to go from one side to the other. So it's locally really good, but it's globally maybe not so good. If you want, and this is completely my interpretation now, you can now think of it like someone would have a kind of a regular brain network, if you want, if they could do some specific tasks really good, but actually would suck in most more like real world tasks, if you want. And the random network is kind of exactly the opposite. Locally, it's really bad. So the clustering is really low, but globally it's really good. So to go from one point to the other is pretty much kind of immediate. So it's kind of the opposite, right? The brain is really bad in kind of specific tasks, but really good in general tasks. And we all kind of know that our brains are kind of in between, right? You can find a good balance. Our brains are really good sometimes in doing specific tasks, and our brains are really good in doing kind of general tasks. So it's kind of not surprising from this point of view that it actually is a small world network. And something in the brain very often tends to be small world networks. This was just my interpretation. So the general interpretation, as far as I know, is still, of course, open, but this was just my interpretation. So what they actually did in the paper, as I said, linked in the description, they did something honest, and not just waffling around like I just did. So they measured a certain thing in the brain. I'm not sure what it is. It doesn't really matter, but you can see. So path length is here, and clustering coefficient is here. The lattice will be here. So high clustering, high path length. The random graph will be here. Low clustering, low path length. And they realized that, oops, whatever we measure is pretty much in between. So it's pretty much a small world network, because that's the whole point, right? This graph is really nice. Small world networks are in between the random and the regular ones. That's kind of the main idea. Okay, let me wrap up. So this very famous experiment, the small world experiment, remember the one where they don't send around emails because it's the 60s, or no, whatever, messages on Facebook or whatever. It's the 60s. They send around honest letters, and they realize that there's kind of roughly 5 steps, 6 degrees of separation between people in the United States. That's what the experiment was all about. And it was rediscovered, or discovered then afterwards, that this holds not just for sending letters around in the United States, but it's kind of a more general principle, the small world principle. Not everything is small world, but a lot of things are. Whatever. Collaboration distance, the brain, Wikipedia, and so on, right? Facebook for sure is, whatever, any social kind of network probably is a small world network. And the way to make this mathematically precise is this funny idea of a small world is in between very ordered and very chaotic, right? It's a 0.5 kind of on this little two-dimensional graph from this brain paper is really kind of obvious. There were random graphs clustering in one corner. There were regular graphs clustering in the other corner, and the small world networks are kind of in between both. And I think that's a pretty cool idea. And as I said, the corresponding paper who defines it, links in the description, about 20 years old by now, and it has just 40,000 citations or something, which is very, very impressive, actually. Anyway, I hope you enjoyed the video, and I also hope to see you next time.